Questions 3 and 4 on the momentum homework both involve inelastic collisions and then questions that have to do with energy. So if we look at question 3, it's about a football player catching a football. And this may not seem like a collision, but we have two objects that are moving at different velocities before something happens, which is the catch, and then two objects that are moving together after the catch, which we'll consider to be our collision. So if we look at before the catch, we have mass 1, the football, moving at some initial velocity, and then the player is moving at some initial velocity. So they both have momentum, so we're going to have an initial momentum there, P initial, and then afterwards we could treat them as if they're a single object that has mass m1 plus m2 moving at some unknown final velocity. Right, and so that's what you're looking for. So you need to, so they have the object's mass now is the mass of the ball plus the mass of the player, right? So you can treat them as a single object, and then you're going to have some momentum P final, and those two are equal to each other. And so that's how you can solve for the final velocity of the player after they make the catch. Now there's two separate situations. In one case, the player and the ball are moving in the same direction, right? So you take that into account. It helps to draw a picture and have your plus sign. So here I chose positive to be the right. And then for the other situation, we'd have the initial velocity of the player be, say, to the left, right? Now it's just asking for magnitude of velocities in the final picture, or in the final answer that you're given. But as long as you choose the ball and the player to be moving, in different directions, then you'll be able to figure out the final velocity. And then when you have to look at the change in kinetic energy, we can just say, well, before you'll have some KE1, which is just the kinetic. You calculate the kinetic energy of the ball, right, using 1/2 mv squared for that, and the kinetic energy of the player, 1/2 mv squared, and then you'll have some final kinetic energy. Now we know that because this is an inelastic collision, the kinetic energy is not conserved, and specifically the kinetic energy is going to decrease in both of these cases. Right, so it's just, all these collision problems involve conservation of momentum, right? So you just need to know the initial momentum and the final momentum. Now, the problem 4, where we have a bullet that's fired into a block, the block and then bullet together are embedded, and they compress a spring a certain distance. And what we want to know is the initial velocity of the bullet. Now this is very similar to the ballistic pendulum problem. So you can go back, I shared a video that shows how to solve the ballistic pendulum. And in that case, you have a bullet that's fired into a block and then that block vertically rises a certain distance. So that's going to be, everything ends up as gravitational potential energy. Here everything ends up in the gravitational potential energy of the spring. Right, so again we have to divide this into, there's an inelastic collision, and then there is conservation of energy after that collision. Right, so the inelastic collision has to be solved with momentum, and then conservation of energy connects the rest of it. So we actually have to work backward because we know what happens in the final case, right? So you would take here, the energy at this point. Well, the spring is compressed as far as it's going to go. So that means that all the energy that we have at this point is the potential energy of the spring. And then here we have an object again, combined masses, because the bullet and the block are stuck together. So here, right after the collision, we'll have some kinetic energy. That's energy 1. Right, so because there is no friction involved, we can use conservation of energy to say that that these two are equal to each other. So from that, you can find the kinetic energy of the block and bullet together, and then that'll give you a velocity, say v2, which is the velocity after the collision. Right. So then you can use that velocity and do a momentum problem with the bullet. Right. So then you would have the momentum of the bullet mass times that initial velocity, which is what you want to know, is going to be equal to the momentum of the block bullet that you can get from this kinetic energy. Right, so you find the potential energy from the spring, convert that to a kinetic energy of the block and bullet together, use that to find a velocity of the block and bullet together. Then you take that velocity and now you do a momentum problem, right? So you're going to use that momentum problem and you'd say, well, I'm going to have V initial for the bullet. I'm going to have velocity equals 0 for the block, and then there's a collision, and then that block-bullet combo, which has a mass of little m plus big M, has a velocity v2, and so then you just using the conservation of momentum, you've got P initial is equal to P final. Right, so you actually have to work backward in time. So once you have that P initial, then you can find the initial velocity of the bullet. Again, I highly recommend checking out or going back to the ballistic pendulum example problem that I shared, because it's a very similar setup. It's just a different type of potential energy in the end. And I can't remember, but whether that starts with at the end with giving you the potential energy and working back to the speed of the bullet, or starting with the speed of the bullet and figuring out how high the block rises. But again, it ends up using all the same concepts.